Here's the introduction to section 2.9. We're going to learn how we can use tangent lines and equations of tangent lines to learn more about some functions. So we're going to start here by finding the equation of the tangent line to square root of 4 plus x at x equals 0. So to do that, we need to find a point and a slope. So to get our hands on that point, we would need to know what f of 0 is, and that's the square root of 4 or 2. So the point that our tangent line goes through is 0, 2. But now we need a slope, so to find that slope we're going to need the derivative. Okay, well I'm going to think about f of x then as 4 plus x to the 1/2 power. So the derivative is 1/2 times 4 plus x to the negative 1/2. And then technically I'm using the chain rule, so I have to multiply by the derivative of 4 plus x, but that derivative is just 1. Okay, the slope of our tangent line then is going to come from evaluating the derivative at 0, and that is 1/2 times 4 plus 0, or 4 to the negative 1/2. But 4 to the negative 1/2 is also 1/2, right? This is 1/2 times 1 over the square root of 4. So that gives us 1/4. So now we have a tangent line that goes through 0, 2 with slope 1/4. So let's write down that tangent line. It looks like y minus 2 is equal to 1/4 times x minus 0, or we can simplify this. Y is equal to 1/4 x plus 2. Okay. How could we use that tangent line we just found to estimate the square root of 3 9/10? Oh, okay, well let's think about this. The square root of 3 9/10, well that's the same thing as the square root of 4 minus 1/10. And I did that because I was asked to use the tangent line, so I'm trying to relate this to the function above, f of x being the square root of 4 plus x. Okay, so that means that this is f of negative 1/10. Okay, well, let's see. Let's think about this. We have the tangent line at 0 to this square root function. So this function looks, let's see, the square root of 4 minus x. Let's see, at 4 it's 0, and it's doing something like this. And we found above, we found the equation of this tangent line at 0. That's not perfectly drawn, but if we look around the window here, around where we have that tangent line, the function will behave very much like the tangent line. So another way to say that is I could say that f of x behaves very much like 1/4 x plus 2 for x is near where I found that tangent line, near 0. All right, well, we have an x here near 0. It's f of negative 1/10. So that would let us claim that f of negative 1/10 is approximately 1/4 times negative 1/10 using the tangent line plus 2, or that f of negative 1/10 is approximately negative 1/40 plus 2, so 1 39/40. And f of negative 1/10, if we go back up here, that is just another way to write the square root of 3 9/10. So we would say this is approximately the square root of 3 9/10. Okay, what did we do? We found the equation of the tangent line at 0, and we used the equation of that tangent line to estimate the output of the function around 0. I think if you were to open a calculator right now and take the square root of 3 9/10, find that as a decimal, and 1 39/40, you see that those agree to a few decimal places at least. So the tangent line does a good job of estimating the function here. Okay, let's generalize this idea. So what is the equation of the tangent line to a function at a? Okay, so at some value a, the tangent line goes through the point a, f of a, just like above it went through 0 and f of 0, which was 2. And it has a slope that is given by the derivative evaluated at a. The derivative evaluated at a is the slope of the tangent line. So the tangent line looks like y minus the y coordinate of the point is equal to the slope times x minus the x coordinate of the point. And we could simplify that ever so slightly. Y is equal to f prime of a times x minus a plus f of a. Okay, so if f of x is differentiable at x equals a, then f of x behaves like its tangent line for x near a. The tangent line then is called the linearization of the function. So if we find the equation of the tangent line at some value, we can, I don't know why there's an extra 4 in here, ignore that. If we find the equation of the tangent line at some value, we can use it to estimate the function near that value. Okay, so let's do an example here. Here's a function, f of x is sine of x, and we want to find the linearization at x equals pi. Fancy word, find the linearization. What is that really saying? Find the tangent line to f of x at x equals pi. Okay, we can do that. So we need a point. Our point is pi, comma, sine of pi. Sine of pi, let's see, if we look at the unit circle, at pi we're at the point -1, 0. So sine of pi is 0. And then the slope of our tangent line is going to come from the derivative. So f prime of x, the derivative of sine, is cosine of x. Sorry about that. The derivative of sine is cosine of x. We need to evaluate that at pi. Cosine of pi, well, it's going to be the x coordinate of that point, so that is -1. Okay, so the slope of our tangent line is -1. It goes through the point pi, comma, 0, and so the tangent line is given by y minus 0 is equal to pi, whoops, sorry about that, is equal to the slope, which is -1 times x minus pi. Okay, so we would bring the 0 over to the other side, and we would say the linearization would be that f of x is approximated by -1 times x minus pi plus 0 for x near pi. So if we wanted to find an estimate for sine of x, since f of x is sine of x, it's approximately -1 times x minus pi for x near pi. So you could evaluate this at 3.2 or something and get an approximate value for sine of 3.2. We'd have to use an estimate for pi, of course, but we could do that. Okay, one more idea here called the differential. In general, if y is f of x is differentiable, then dy is equal to f prime of x dx. Okay, and let's see if we can draw a picture. So dy dx would be f prime of x, and if we just think about operating with these things, dy would be f prime of x dx. Okay, these things are both called differentials. And what's really happening here is if we look at some function, and we have some tangent line to that function, right? And then we look at some small change on the x-axis, which is going this way and this way. Let's see if I can blow up on that for a second. Okay, here is some small change on the x-axis. It results in some small change on the y-axis. And when we do that, dy dx is the slope of the tangent line. Right? Change in y divided by change in x. And so dy dx is equal to f prime of x, or dy is f prime of x. Oops. dx. Okay, so what we can use this for is to see if we have some small change on the x-axis with a function, with the input to a function, what is the corresponding small change on the y-axis? That's another way to estimate what's happening with functions. So here's a generic example, and then we'll do one that's set in context. If y is 3x cubed plus 6x squared, find dy when x equals 1 and dx is equal to 0.1. Okay, so dy is going to be f prime, which is 9x squared plus 12x dx. Okay, let's see. And so we want to find dy when dx is 0.1 and x is equal to 1. So we get, missed some parentheses up there, we get 9 times 1 plus 12 times 1 times dx, which is 0.1 or 1/10. So dy is 9 plus 12, 21, geez, times 0.1, which is 2.1. Okay, what does that really mean? It means that a 0.1 unit change on the x-axis should result in a roughly 2.1 unit change on the y-axis when we're near x equals 1. Okay, so if x is 1, y is equal to 3 times 1 plus 6 times 1, or 9. So this tells us that if we move over to 1.1, we move over by 1/10, y should go up by approximately 2.1. So y is approximately 11.1. So we use that little change on the x-axis up here to find the corresponding change on the y-axis to allow us to estimate the value of the function. Okay, let's put that into practice one time in context, and then you should be able to go try to tackle the 2.9 activity. The radius of a circle increases from 5 to 5.2 inches. Estimate the resulting change in the area. Okay, so we have radius 5 to radius being 5.2. So we've had some small change in the radius. I'll call it dr of 0.2 inches. And we want to learn information about the change in the area. Well, the area in relation to the radius is pi r squared. So the derivative of area is the differential of area is 2 pi r dr. Right, you could have done an intermediate step in here. dA dr, take the derivative with respect to r, is just 2 pi r, multiply both sides by dr. To work with the differentials. And so we've been asked for the change in area, so we've been asked to find dA. So dA is 2 pi times the radius, which was 5, times the change in radius, which is 0.2. And what does that equal? 10 pi times 2/10. That looks like 10, huh? Or, sorry, 2. 10 pi times 2/10 is 2 pi. So that looks like 2 pi. And what would those units be? That would be square inches. So another way to interpret what we just learned is that when the radius is 5 inches, we know the area is 25 pi. And we've just learned that when the radius is 5.2 inches, the area is approximately 25 pi, plus it goes up by 2 pi, 25 pi plus 2 pi, or 27 pi square inches. Okay, see if you can use that to tackle the 2.9 activity.